Radio, looking at molecules with 5 electron sets around the central atom. So here's our total number of sets. Here's our number of bonding sets, which leads to 5 shapes, but I've only shown 4 here because when you only have one bonding set, you have a linear atom. So 5 electron sets and 5 bonding sets makes a trigonal bipyramid. And you can see on this 3D diagram here we have 1, 2, 3, 4, 5 sets around the central atom, electron sets, and 1, 2, 3, 4, 5 of them are bonding, leading to the trigonal pyramid shape. They are called trigonal pyramid because they sit inside, they will fit nicely inside this trigonal pyramid shape here, which is like 2 tetrahedras joined on one face, and in each of the corners here will be an atom of the molecule, and that leads to this shape being called a trigonal bipyramid. And if I manage to actually get this open, we'll see that the atoms in the molecule fit nicely into the corners of this shape. If I can get that open. So there we go. We have the central atom, and then we have 1, 2, 3, 4, and down the bottom we have 5 outer atoms. And that leads to something quite unusual. We've got 2 different bond angles in this molecule because there's 2 types of positions the outer atoms can be in. This one here and this one here, 2 of them are called polar positions, as though this was the Earth. This would be the North Pole, the South Pole, and of course what do we have around the middle? We have the equator. So these 3 here are called equatorial positions. The angle between a polar and an equatorial atom or bonds is 90 degrees, and you get 1, 2, 3 of those angles up here and the same number down the bottom. The angle between any 2 of the equatorial atoms or bonds is 120 degrees. We have 3 bonds poking out in that circle, making a 120 degree bond angle between any 2 of the equatorial ones. Okay, so that shape is the trigonal bipyramid. Then we move on to having 4 bonding sets, and that shape is called the seesaw shape. 5 electron sets, 4 bonding, seesaw. In this diagram I've shown the non-bonding pair, which in a shape diagram really shouldn't be there. So over here I've removed that and I've tipped it over onto its side. This is SF4, and you can see if a person sat there and a person sat there, they could rock back and forth like a seesaw. And again we have 2 different bond angles. We still have 4 bond angles that are at 90 degrees, but we only have 1 bond angle that is at 120 degrees because there's only 2 of these equatorial atoms here in the equatorial position there. Okay, and if I put that down, you could see that could rock back and forth just like a seesaw basically. Moving on, we have 5 electron sets and 3 of those being bonding. We move to a T shape. So here we have that situation. Still got our 5 electron sets, 1, 2, 3, 4, 5, represented by the toothpicks, and then we have, and that gives us our T shape here, and we have 2 non-bonding sets here. And as we know, the push or the effect of these 2 non-bonding pairs will actually push those those bond angles down below 90 degrees and close them up a little bit. So that is the T-shaped molecule. And going on down to having 5 electron sets, 2 of them bonding, we have the linear shape here. And we still have the 2 polar position atoms and bonds make a 180 degree bond angle. If those outer atoms were the same identical atoms, we have these 3 lone pairs sitting around the middle there. That would be a very nice exact 180 degree linear molecule. And an example of that, good example that most people have come across, is the triiodide ion here, which I3 minus. That is the brown colour in iodine solution. When you put iodine into a solution of iodide to dissolve it a bit more, you get the triiodide ion. Also ICl2 minus ion, XEF2 also linear but with 5 bonding sets. Okay. So down here is just a diagram to show you the different positions here. So these two, which are straight opposite each other in a straight line, they are the polar position atoms, and down here we have in green the equatorial positions around there. And that is 5 electron set shapes.